Okay, welcome back to EE210B. We are going to continue our discussions of stochastic gradient algorithms. We finished covering part 2 of the course, which deals with single agent adaptation and learning and optimization by a single standalone agent. Today I will cover part 3, which deals with centralized processing. Okay, what if you have, for example, a fusion center that's able to collect the information from multiple agents and then run a centralized algorithm? What kind of performance can we expect, and how does it compare to the single agent case? Okay, so this is the theme of today's lecture. Okay, so this is part 3, centralized adaptation and learning. And it's based on chapter 5 from the text that I indicated to you earlier. Okay, so in the last lecture, I derived these expressions for the performance of a single agent running a stochastic gradient algorithm. Right? I'm trying to minimize a strongly convex function using a stochastic gradient algorithm. And if you let it run to steady state and for small step sizes, we showed that the mean square deviation, which is essentially a measure of the size of the second moment of the error vector, right? This quantity in steady state will approach that value mu over 2 trace of H inverse R sub S, where H is the Hessian matrix of your cost function at the optimal location, and R sub S is the covariance matrix of the gradient noise in steady state, right? So that's what we derived last time. So just to remind you, so this R sub S is the covariance matrix of the noise process Si at omega O, Si transpose at omega O, condition on the past, right? And the limit of this. So it is the steady state covariance of the gradient noise, right? So I mentioned to you earlier that these two parameters, H and Rs, are critical in characterizing the behavior of stochastic gradient algorithms. The first measure is the mean square deviation, and the second measure is the excess risk, and that is measuring how far the cost is from the minimum cost on average in steady state, right? Again. So you see, these are the expressions. This is for the case of real arguments omega, and then you have similar expressions for the case of complex arguments, where I explained that H becomes 2m by 2m, and this Rs is replaced by extended covariance matrix. And the convergence rate, the rate at which the mean square error approaches this steady state value, is given to first order in mu by this expression here, 1 minus 2 mu lambda min of H, right? So this is what we derived last time for a single agent running a stochastic gradient algorithm on its own, right? Implementing this recursion here. Gradient relative to W transpose, and similarly for the complex case where you compute the gradient relative to omega star. Very good. So let's look at an example and use it as a motivation for what's going to come later. Okay, so let's consider the case where I have a streaming sequence of data d of I with variance sigma d squared, right? We considered this example several times before. Ui is a streaming sequence of row regression vectors with covariance matrix R sub u, denoted by R sub u, and it's assumed to be positive definite. And the second order moment connecting d to u is denoted by little r sub du, and the data satisfies this linear regression model. And then we formulate the mean square error estimation problem to recover omega 0 from knowledge of d and u, right? This is the mean square error of cost. If you find the omega that minimizes this cost, you get exactly the omega 0 that you are looking for. And because we don't know Ru and Rdu, meaning we don't know the statistical distribution of the data to figure out what these moments are, we cannot use the traditional gradient descent algorithm. Instead, we use a stochastic gradient descent algorithm where you compute the You approximate the gradient vector by using this expression here. You simply differentiate the loss function and you end up with the LMS algorithm, right? This is just a quick reminder, okay? And now if I apply the performance expressions to this algorithm, right, for this particular algorithm, we know what the gradient noise is, which is the difference between the approximate gradient and the true gradient. And we saw last time that this is the expression for the gradient noise in this case. And if you evaluate it when omega I minus 1 is equal to omega 0, you will find that the gradient noise is simply given by this last expression, right? This last term here. And therefore R sub S will be the variance of that. And we already know in this case the Hessian is 2RU, right? So if I compute what the MSD is, for example, the MSD is mu over 2 trace of H inverse RS. We did this calculation last time. You see that H inverse will have RU inverse and RS has RU, so that cancels out. And when you plug these values into this expression, you will find out that the MSD, right, using this H and that RS is given by this expression, and the excess mean square error, or the excess risk, which in the context of adaptive filtering we refer to it as the excess mean square error, okay, because this quantity is a mean square error, and this difference is how much in excess of the minimum value you have. So in the context of adaptive filtering, we refer to it as the excess mean square error. When the cost function is a mean square error, that's what you get, okay? So we derived these expressions before. Very good. So this is a summary of the performance of standalone agents, okay? Very good. And we have similar expressions, of course, for complex valued data, okay? You will add an additional factor of 2 will appear in these expressions. Very good. So now what I'm going to do today, okay, I'm going to consider two scenarios that involves a multitude of agents now, okay, a multitude of agents. One of them is the non-cooperative scenario, and the other is the centralized scenario. Okay, so what that means is the following. So now I will have a collection of n agents. In the non-cooperative case, I have a collection of n agents. Each one of them is trying to minimize its cost j sub k of omega. So now I'm going to use the letter k to refer to the cost that's associated with agent k. Okay, so k becomes now the agent index, and it varies from 1 to n, right? So far in the course, we only had a single agent. So let's assume that now I have n agents, and each agent has a cost function associated with it. These cost functions, they can be the same, right? So j sub k of omega, they could be the same, in which case they will all be the same j omega across the agents, or they can more generally be different across the agents, okay? In the non-cooperative scenario, okay, I'm going to assume that all these costs have the same minimizer, okay, the same minimizer omega 0, okay, in order to allow for meaningful comparisons, okay? So if I have a multitude of n agents, each one working on its own, trying to estimate the same parameter, then the comparison among these agents becomes meaningful because they are all trying to solve the same problem, okay? So remember that, okay, in the mean square error case, this cost will look like minimizing the mean square error using the data at agent k, which I'm going to denote by d sub k, u sub k. So now I add a subscript k just to identify that this is the data, d of I, u of I, that occurs at agent k. So if the cost function happens to be the minimum mean square error cost at agent k, it will look like this, right? In this particular case, the covariance, which I called RU before, will be RU at node k, and the cross correlation, which I called RDU, it will be RDU at node k, right? Okay. Of course, if the cost functions are the same across all agents, these will be the same. They will be independent of k, right? And the omega 0 that minimizes this cost, right, is given by, we already know, is given by RUK inverse times R DUK, right? This is what we know. So when I say all cost, if I say that I'm dealing with a situation where these costs have the same minimum, then in this particular case, in the mean square error case, that essentially amounts to saying that these quantities evaluate to the same value. Okay, this is just an example, okay, but the analysis will be more general than that. So in the first case, I have a collection of n agents working, each one working on its own, independently of the other. In the second case, I have n agents, but these n agents are going to send the data they have, the dks and the UKs they have, to a central location that's going to process it, okay, and figure out what the omega is in the manner I'm going to describe, okay? So let's start with the non-cooperative case first, okay? I'm going to illustrate it first for the mean square error case, and later I'm going to generalize for general cost functions, okay? And I'm going to deal with the case of real data, real omega or complex valued omega simultaneously. So I can do that just by introducing this type variable that I explained to you many times before. So the expressions, the performance expressions for the MSD, for the ER, or for the convergence rate, they will always include this H. If you are dealing with real data, you replace it by 1. If you are dealing with complex data, you replace it by 2, right? So I'm going to do both cases simultaneously, okay? So let's consider first the case that where I have n agents. So K will be the index that I use to label agents throughout this course, and capital N will be the number of agents throughout this course, okay? And initially I'm going to study the case of mean square error estimation to illustrate the main idea. So every agent is receiving a streaming sequence of data. Now I attach the subscript K to it, okay? Very good. And I'm assuming that the data at every agent satisfies a linear regression model like that with the same omega 0. So each one of them is trying to estimate omega 0 using its own data. So each one of them is going to run its own stochastic gradient algorithm on its data, right? The variance of the noise at node K, I called it before sigma squared V, now I'm attaching K to it, okay? So all variables now have a subscript K just to indicate that these are quantities at location K, at agent K, okay? And the covariance of the regression data, if you are dealing with real data, it's defined like this. If you are dealing with complex data, it's defined like this. This is just a reminder, okay? Okay. So let's assume, okay, in this initial example, okay, that the covariance matrices are uniform, okay, and this is just an example, a motivating section. Let's assume that the covariance matrices are uniform across the agents, okay? This means that the Hessian matrices are the same across the agents, right? All of them, the Hessian matrix for agent K will be 2RU, so the Hessian matrices are the same. Very good, okay? Okay? And because I'm dealing with mean square error costs, obviously the Hessian matrix, which is a constant, will be bounded from below and from above by some nu and some delta. And these are related to 2 times the lambda max of RU, 2 times the lambda min of RU, right? Okay, so this condition is satisfied because the performance results we derived last time, they assume that this condition is satisfied. So I'm just reminding you that it is satisfied in this case. Okay? And this is the nu and this is the delta. And then each node now, each agent is running its own stochastic gradient algorithm. You see, this is the same algorithm we wrote before. The only additional thing that appears here is the K. That's all, meaning that this algorithm is running at location K, agent K. Okay? So you have a collection of agents spread over many locations, right? And each one of them, so this is agent 1, agent 2, agent 3, agent K. So each one of them is running the corresponding algorithm based on the data, because each one of them is receiving, let's say this is, let's say D5 and U5, right? U is a vector, so I use a subscript to index time, and D is a scalar, so I use parentheses to index time, right? This is my convention. Very good. So now, if each agent runs an algorithm like this, what would be the performance of each agent? Well, just write down the expression we derived before for the LMS case, and this is the expression. I just showed you an example earlier in the real case, right? So this is the MSD performance at agent K in the non-cooperative situation, okay? So I'm using ncop there just to emphasize that the agents are not working together. They are separate, so this is non-cooperative. So this is the performance, right? Mu times the size of the regression data, or the size of the filter, times the noise at location K. If you are dealing with real data, H is 1. If you are dealing with complex data, H is 2, right? So H is just a constant, don't worry much about it, okay? And the convergence rate, at which rate you will arrive at that steady state value, it's given here, lambda min of the Hessian matrix, which is 2 lambda min, so that's why you had 2 mu here, it becomes 4 because 2 comes from the lambda min of the Hessian. And the Hessian is 2 RU in this case, divided by H, okay? So now what you observe from this result, okay, is that, remember, all of them in this particular example are estimating the same omega 0, right? So some nodes will perform better than other nodes because the performance is proportional to how much noise you have at location K. And some locations may have more noise than other locations, right? So you see from this result that the performance is dependent on the noise profile across the agents, okay? So it's not the case that they will all be equally accurate in estimating omega 0. Some of them will do better than others, will get closer to omega 0 than others, okay? Very good. So this is a summary of what I just said. In the non-cooperative case, mean square error case, and a similar result will hold in the general case when the cost function is not necessarily the mean square error cost. This is the performance of agent K. It converges at this rate, and the conclusion is that agents with noisier data will have larger MSD, therefore worse performance, worse MSD than agents with cleaner data. Fine?
All of them will converge at the same rate, right?
Yeah, all of them will converge at the same rate because we assumed RU is uniform. They all converge to the same rate, right? The MSD, if you were to plot the MSD, right? So if the vertical axis is the expected value of W tilde at node K over time, right? So they will all be converging at the same rate, right? But some will converge to a lower level, others will converge to a higher level, and so forth, okay? So this is simple. This is just direct application of what we learned in the previous lectures. Okay. And now, if you want to note, okay, what's the average performance across my agents? So just add the performances. This is a constant, and divide by n, right? So you see that the average performance over this network of non-connected nodes, right? Unconnected nodes is proportional to the average power across the collection of agents, okay? The question, can you do better? Of course, right? Once we start adding cooperation, when I talk about centralized solutions, that's one extreme case of cooperation where you have access to all the data from across the agents. I'm going to see how this improves, right? And then in the later part of the course, when I just have a topology where agents can only see a subset of other agents, those that are in their immediate neighborhood, okay, can I improve the performance relative to this? And you will see that we can, okay? Very good. So I have a simulation here, okay, here I'm just describing the simulation. I'm averaging over 2,000 experiments, okay, and plotting, right, averaging the learning curves, right, the mean square error curves over 2,000 experiments to generate the expected value over time, okay, and M is 10 in this case. The step size is the same across the agents, okay, because the performance expression depends on the step size, right? Just keep that in mind. So I kept mu constant across the agents, otherwise that will affect the performance, okay. RU in this case is that, and the noise, okay, so here I'm running 2 agents. One of them has more noise than the other. Then, of course, if you plot this curve, if you plot the curves, you will get something like this, right? For one agent, which has noise 0.032, okay, which is higher than the noise of the other agent, 0.01. Obviously, you can see they converge at the same rate, but one of them converges to a higher MSD value than another. And these horizontal values, they match exactly the theoretical expressions, right? The horizontal lines are the values that you get from your theoretical mu times m times sigma v squared for each one of them. And you can see that they indeed converge there. So the theoretical expressions give you very good, right, match for what you obtain from simulations, right? And okay, very good. And there is a big difference here in performance, right? Almost what, 5 dB perhaps, right? In performance. Okay, so now let's go to the second situation. Again, I'm still focusing on the case of mean square error estimation, okay? So now I have n agents, but let's assume that these n agents, here it is, I still have n agents, right? But now the n agents, they are not doing any processing locally. They take their data and they send it to some remote fusion center. It doesn't need to be remote, but to a centralized location, right? And then that location runs a stochastic gradient algorithm. Okay, so what kind of an algorithm does this? So these are the nodes, right? And this is the fusion center somewhere here. They send their data. That's all they do. They send the data, right, the D's and U's. And this location is going to run an algorithm, this centralized algorithm. Okay, now, so what this is going to do, so what the algorithm is essentially doing, remember that this is the approximate gradient used by agent K, right? This is the approximate gradient used by agent K. So essentially what the algorithm is doing in this case, it's averaging all approximate gradients, right? Getting from it, let's call it an improved gradient direction, and then move along that direction to update omega. Okay, so that's what the centralized solution is doing. Since I have, right, multiple approximations for the gradient direction, let me average them and move along that direction, okay? So you can see that at every iteration I, this centralized solution is using the entire data that you collected from all agents, whereas in the non-cooperative solution, every update at every agent is only using one piece of information, one D, one U. Here you are using n at a time, and I'm averaging them, okay? Fine. So what kind of performance can we expect from an algorithm like this? Okay. So this is what I explained. What you have there is the approximate direction, gradient direction at agent K, and what you are doing is averaging them, okay? We are going to show, here I'm just putting the result, but the theorem that I'm going to prove later in this lecture will tell you that this is the result, that the MSD for this centralized solution, okay, because the centralized solution, after all, is a stochastic gradient algorithm. The new weight is the old weight, and this will play the role as an approximate gradient, and I'm going to show you that for some function, okay? And therefore, I can apply the results from previous lectures to this algorithm, because I'm going to show you that it can be interpreted as a stochastic gradient algorithm for some function j, okay? Actually, the function j, I'm going to call it j global, of omega will be the sum of the individual functions, such that the gradient of this function is the sum of the gradients of these, and the approximate gradient for this is related to the sum of the can be approximated by the sum of the approximate gradients for the individual costs, which is what you have here. So I'm going to show you later that for this particular case, the MSD will be given by this expression that you have here. And the convergence rate is given down here. Now, if you compare the convergence rate with what we had in the non-cooperative case, each individual agent and the centralized solution, all of them have the same convergence rate. So the convergence rate is still the same. But what about the MSD level? Of course, it is still the same if you implement your centralized algorithm in this manner, okay? Where I added the 1 over n here to play the role of an averaging factor here, okay? So while the individual non-cooperative solution used mu, the centralized solution is using mu over n, okay? Very good.
So can
Yes.
you think this as uniform weighting for the delta?
Yeah, I'm coming to this remark at the end of the lecture, okay? At the end of the lecture. Good point. Yes, okay. So the convergence rate is still the same, but what about the MSD? If you compare this expression with what we had before, in the non-cooperative case, when I average the performance across the agents, I had the mu over h times m, and I had the average noise power, but I did not have this factor here. I did not have the 1 over n factor. So you see that the centralized solution improves the MSD by a factor of n, right? By a factor of n. So that's, right? Depending on the size of n, this can be a significant improvement, right? This is over the average performance. Okay, so this is a summary. Here it is. On the right here, I have the expression for the average performance over the collection of non-cooperative agents, all of them trying to estimate the same omega 0. You can see it's the average noise power times the factor. Here it is the average noise power times the same factor but divided by n. So you have an improvement of n times, okay? The convergence rate continues to be the same. Of course, I did not prove these results. These require proof, and that's what you will see in the later part of this lecture. For now, I'm just motivating it, okay? Okay. So now, the centralized solution, therefore, provides 1 over n times improvement, right, over the average non-cooperative solution, right? Okay. Very good. So you have an n-fold improvement in MSD, right? But what about the individual agents, okay? What I mean is the following, okay? So before I get to the second point, let me show you the expression, the simulation, right? The red curve is simulating a non-cooperative agent, one non-cooperative agent, and the blue curve is simulating the centralized solution, averaging, of course, over multiple experiments. In this particular case, it says here 2,000 experiments, right? And it tells you what values of noise power, RU, and so forth I'm using, okay? And you can see there, and this improvement in performance is, in this particular case, n is 20. So 10 log 20 in dB, it will give you this difference here, okay? Okay, now, so this is just this slide is just explaining how the figure was generated, okay, and how the data was generated, fine, okay, so that's, I can skip these slides, okay, and this is the improvement that you will get. Difference will be 13 dB, which is what you see in the figure. This difference here is about 13 dB, and you already know where it comes from, the factor 1 over n, okay. That was the first observation. Therefore, on average, you improve by a factor of n. Very good. But now comes another point which is important. So these are, let's say I have 4 non-cooperative agents. Each one has its own noise, right? Sigma v squared 1, sigma v squared 2, and so forth, right? So, and here I have the centralized solution. This will be the average solution by a factor of n, okay? But will the centralized solution be better than every individual non-cooperative solution? And the answer is no, not necessarily. Not necessarily. Why? Let's take a simple example. Okay, here let's assume I only have 2 agents. I only have 2 agents. Okay, one agent has noise power sigma v squared. The other agent has much worse noise power 5 sigma v squared. Right. So what's the non-cooperative performance? It will be mu over hm, right? This is just a constant, right? So let's just call it a C, a constant, times the average noise power. The average noise power here will be 3 sigma v squared. So this is the non-cooperative. Okay, what about the centralized solution? It will be the same constant, but divided by 2. So you will get 1.5, okay, sigma v squared. This is the centralized solution. Okay, what about this individual agent on its own? You will get the same constant times sigma v squared, And what about this individual agent on its own? You will get constant times 5 sigma v squared. So you can see that the centralized solution is always better than the average non-cooperative, but it can be worse than some individual agents, right? So it's not always true that this centralized solution will perform better than every individual non-cooperative agent. On average, the performance will definitely be better, okay? But because you have an averaging effect and you are dividing by n, it can end up, especially in situations where the change in noise profile is so drastic between agents, it may be the case that the average performance you are getting in the centralized solution is worse than the best single agent, right? Okay, so this is a remark I wanted to make, okay? Very good. So now, let's study this problem under more general conditions and not necessarily for the mean square error case, okay? So I have a collection of agents, n of them. Each one has a cost j sub k of omega, okay? Where j sub k does not need to be the mean square error cost, which is what we did in the previous slides. So let's keep this more general, okay? And I associate with these agents a global cost, which is an aggregate cost, meaning you add up all these individual costs, okay? So the centralized solution that I'm going to develop is a stochastic gradient algorithm for minimizing this global cost, okay? This aggregate cost. We already know how to write down stochastic gradient algorithms to minimize, if each individual jk is strongly convex, I can write down the corresponding stochastic gradient algorithm at node k to minimize it individually, right? But now I want to solve this problem of minimizing an aggregate cost. So I'm going to assume, so whenever we have an aggregate cost, and we are going to have it in the network context, okay, we are going to assume that the aggregate cost satisfies conditions similar to what we talked about before in the individual cost case. Okay, so let me mention the conditions and then I'm going to make a remark, okay? So now I'm interested in developing a stochastic gradient algorithm for the global cost. So I'm going to assume that this global cost is strongly convex, so it's bounded from below by some, so I call it nu c for centralized, okay? So this is the lower bound for this centralized cost, aggregate cost. Lower bounded by nu c, upper bounded by delta c. I also assume that the Hessian is Lipschitz, okay? Because we needed these conditions when we derived our performance expressions, if you remember from the previous two lectures, okay? So the condition 20, the first condition on this page is guaranteeing that the global cost is strongly convex. I'm not requiring now anymore the individual costs to be strongly convex. Because if you want to develop a stochastic gradient algorithm to minimize the global cost, all we really need, based on the theory we have developed so far, is for this global cost to be strongly convex. The individual costs, they do not need to be strongly convex. It's enough for one of them to be strongly convex, for the aggregate cost to be strongly convex. Because remember, if you come here to the definition of the aggregate cost, the Hessian of this is the sum of the individual Hessians. If one Hessian matrix is lower bounded from below, that's enough to guarantee that the global Hessian is lower bounded from below. Okay, so I don't need all individual costs to be strongly convex. One of them being strongly convex is enough, right? So that's a relaxation. Okay, so I'm only assuming the aggregate cost is strongly convex and satisfies the conditions we talked about before. Lower bound, the Hessian is lower bound from below, from above, and the Hessian is Lipschitz. Now, when is it that I'm going to assume that the individual JKs, each one of them is also strongly convex? I'm going to assume that when I want to compare the performance of the centralized solution with the performance of non-cooperative agents. Because for a non-cooperative agent to work properly according to the theory we developed so far, each one of them will be running a stochastic gradient algorithm on its cost. So its cost has to be strongly convex so that it has a well-defined minimum. So it's when I want to compare them together, compare the performance of the centralized solution against the non-cooperative solution, that's when I need to assume that the individual costs are all strongly convex, so that that comparison is meaningful. Understood? Okay. But let's continue with the centralized solution for now. So the global cost is strongly convex. Okay. If it is strongly convex, it will of course have a unique minimizer, which we continue to denote by omega 0. And like I said, I'm not requiring the individual JK to be strongly convex. It's sufficient for only one of them to be strongly convex. Okay? Very good. So now what I'm going to do, I'm going to run a stochastic gradient algorithm on this J global, right? The aggregate cost. Fine. So the stochastic gradient algorithm would look something like this. Minus mu gradient relative to omega star of the J, right? Technically, this is what we would like to do, right? To approximate the gradient of the aggregate cost, right, relative to omega star. Okay. And of course, it will depend on how you evaluate this approximate cost for the aggregate cost. One way to do it is to say, I'm going to use as an approximation for this gradient vector, the sum of the individual approximations, right? That's one way to do it. Okay, one reasonable way to do it. Right? Because the gradient of the aggregate cost is the sum of the individual gradients. So the approximate gradient, I'm going to approximate it as the sum of the approximate gradients. Fine? So this is what I'm doing here, the sum of the approximate gradients, and I'm using as a step size mu over n. So if the non-cooperative solution uses mu, for the centralized solution I'm going to use mu over n. And the reason why is because, as you are going to see, by using mu over n here, the convergence rate of this centralized solution will be the same as the convergence rate of the non-cooperative solution. And why do I ensure that they have the same convergence rate? Because whenever you are comparing the performance of two algorithms, adaptive or learning algorithms, you see, you have a learning curve, right? A learning curve. Let's say this is the mean square error curve, which tells you how the error evolves over time. There are two factors that characterize this performance, at least two factors. One is the steady state value, and the other is the convergence rate. So if you want to compare two algorithms against each other, you have to fix one of them and then compare them in relation to the other parameter. So if both of them have the same convergence rate, then which one is converging to a lower level? Or if I fix the MSD level, which one is reaching that level faster, right? So when you make comparisons, you have to fix one of these parameters and then compare for the other parameter, okay, for your comparison to be meaningful. You understand? Okay, so you are going to see that because of this, and the convergence rate of this algorithm will match the convergence rate of the non-cooperative solution, right? The non-cooperative solution will be WKI minus 1 minus mu, and then you will not have a sum, the gradient of JK, WKI minus 1. That uses a mu, this one uses mu over n, and I'm going to show this matches their convergence rates. Okay. Okay. Now, or you can, if you wish, you can simply call this some mu prime. Okay. And then you can ask the question later, what mu prime should I use so that both algorithms have the same rate? You'll end up having that it has to be this. Okay, very good. In the real case, you do something similar. If you are dealing with real data, you just use the gradient relative to omega transpose. Okay, so there isn't much difference here. Okay. So now, let's do the analysis for this algorithm, derive its performance measures, right, for this centralized algorithm, and then compare with the non-cooperative solution in this general case. Okay. Very good. Now, you see that the gradient vector that I'm using here, the approximation that I'm using, involves several individual approximations, right? So each one of them has gradient noise associated with it, right? At every with every k, I have a gradient noise process, which is the difference between the true gradient and the approximate gradient at that location k, right? Okay. So here it is. So this is the gradient approximation at location k, and this is the true gradient, and the difference, consistent with what we did before, we call it gradient noise at location k. Very good. What would be the overall gradient noise for the centralized solution? It will be the sum of all of these SKs, correct? For k going from 1 to n, right? Because the gradient noise for the centralized solution is the difference between the actual gradient of the aggregate cost, which is the sum of gradients, and the approximate gradient for the aggregate cost, which is the sum of the approximate gradients, right? So all this is saying, if I define these individual gradient noise processes, the actual gradient noise in the centralized solution is the sum of these individual gradient noises, right? Very good. So here it is, okay? And remember, I'm dealing with the general case where the omega can be complex. So the results, I'm going to be presenting them in that general context. And if you remember from the last lecture, I explained to you that when we study the performance of stochastic gradient algorithms in the general complex case, the performance expressions, right? If I just write one of them here, you will remember the performance expressions, they took this form, H inverse, and then you had the extended covariance matrix here, right? RS transpose, something like this, RQ star, if I'm not mistaken, right? And this was the covariance matrix that corresponded to an extended gradient noise vector, okay? So let's define that. This is just definition at this moment, okay? Take that individual gradient noise, extend it, okay, so that it's 2m by 1. And remember, I use the notation E to refer to extended vectors always. Okay. And we define, right, its covariance. This is the covariance matrix, the conditional covariance matrix of the extended noise. And this is the RS and RQ. This is the conditional covariance at omega 0. We used to call it RS when I was dealing with a single agent in all previous lectures. Now I call it RS of agent K. And this is the RQ, SS transpose. So in the complex case, like I explained in the last lecture, I need these two moments. In the real case, you only need one of them, RS, and we defined it with SS transpose, right? It is the real, RS is the real covariance matrix. RQ is not a covariance matrix. It is symmetric, but not necessarily non-negative definite. This one is symmetric and non-negative definite, okay? So you just have to add this Q, that's all, okay? So define these quantities, okay? So these are at the individual agents, okay? Now, since this is the gradient noise for the centralized solution, and the centralized solution looks like a stochastic gradient algorithm, right? This is a stochastic gradient algorithm, has the form of a stochastic gradient algorithm. The new weight is the old weight minus some mu prime step size times an approximate gradient, right? This is the approximate gradient. And we know what the corresponding gradient noise is. I just called it SI, right, of omega, which is the sum of all of the individual SKs, right, at the agents, right? So for me to be, so I can deduce the performance of this algorithm from results I had before on the single agent stochastic gradient algorithm, right? If I can find what the Haitian of the global cost is in terms of the individual Haitians, that's easy, right? The Haitian of the global cost is the sum of the individual Haitians. And if I can find what the covariance matrix of the aggregate gradient noise is in terms of the individual covariance matrices, right? If I can find what the R or the extended covariance matrix of this is, then I have the solution. I just can call upon results from before. So this is what I'm going to do now. So I'm going to find out what the covariance matrix of this noise is, okay, in terms of the individual covariance matrices, okay? So let's do that calculation, okay? So I'm interested in finding RS and RQ. You see, these are the covariances or the moments for the gradient noise, the aggregate gradient noise, SI. There is no K here, right? Because if I know RS and RQ, okay, then I know from the previous lecture that the performance will look something like this: trace of H inverse times a 2 by 2 matrix, right, which contains RS, RQ, RS transpose, RQ star, something like that, if I'm not mistaken, right? Okay, so I need to, so H inverse we know. What is H? What is H? Right? Because J, the aggregate cost, is the sum of the individual costs, right? So the H, which is the Hessian of this at omega 0, right, will be the sum of the individual H's, the individual Hessian matrices at omega 0, right? So this H here I know, right? So you can see right away that this expression is tending to be something like this. Sorry, trace. Here you will have a sum of these individual Hessians inverse, right? And then I have to find what that matrix is, and that's it, right? Okay, you are going to see that this matrix will also turn out to be a sum of the individual matrices, RSK, RQK, and so forth. This is what the theorem will be showing, right? I already found what this is, easy. I still need to argue what this is, right? I'm claiming, and I'm going to show you that quantity, I can write it as the sum of the individual quantities, and then I get the result for my centralized solution, okay? So why can I do this? Because of these assumptions that I'm going to introduce, okay? So I'm going to assume that the individual gradient noises at the agent satisfy these conditions, okay? Now, the first condition and the last condition are similar to what we have seen before, that the gradient noise is zero mean. This is, again, reasonable, makes sense, okay? At every agent, it is zero mean conditioned on the past, and that it's fourth order moment or second order moment, right? We said that if we introduce bounds on the fourth order moment, these imply bounds on the second order moment, right? So these are just similar to the bounds we had before, right? The only difference is now every agent satisfies a bound like this. Every agent satisfies a condition like this, right? So that's why the coefficients that determine the bound now become agent dependent. That's all, okay? You can write it with an omega, or you can write it with an omega tilde here, okay? The two conditions that I'm adding, okay, and you can do without them, as I'm going to explain at the end, but with these two conditions, the analysis becomes simpler, is that the gradient noises across the agents, I'm going to assume that they are uncorrelated. So across the agents, that's the second condition, they are uncorrelated. So you see, if you take any two different agents, K and L, this is the conditional correlation, 0, and that they are second order circular. Okay, so what that means is that in the complex case, SS transpose is 0 when K is different from L, okay? So under these two conditions, I can show that the covariance that I had on the left is the sum of individual covariances that I had on the right. Okay? Now, later I'm going to make a comment that if you don't want to introduce conditions at the level of the individual agents, you can instead introduce conditions at the level of the global noise, SI of omega, given the past is 0, and the second or the fourth moment of this global noise, which was the aggregate noise, given the past, is upper bounded by something like this, right? Let's say some beta bar over H omega to the 4 plus some sigma bar, okay, something like this. You can do away with these 4 conditions and simply, because it's a gradient, a stochastic gradient algorithm with this gradient noise, right? So if you just introduce the conditions at this level, you'll be able to complete the argument, okay? But here, I would like to introduce the conditions at the individual level because this will facilitate comparison with the non-cooperative case, okay? Now, so if you do this, and again, okay, because we needed this assumption that the gradient noises, right? So this is the covariance of the gradient noise. There is no k here, so this is the global, right? It has to satisfy a Lipschitz condition. If you remember, for the stochastic gradient algorithm, we require the condition like this on the covariance matrix of the gradient noise. And we use this condition to derive the performance expressions in the previous lectures. So I'm just introducing it here to be precise, okay? Okay. So all the conditions we introduced before for a single agent stochastic gradient algorithm, you introduce them here for the aggregate cost and for the aggregate gradient noise. That's all, okay? Very good. So now, because of these conditions, it holds that Rs is the sum of the individual S's, Rq is the sum of the individual Rqs. Let's see why quickly. What was Si, right? Si was the sum of the individual S's, right? Very good. So now, what is Rs? For Rs, I have to compute I have to perform a calculation like this, right? Si star, conditioned on the past, right? So you have to compute the expected value of that sum times the sum star, conditioned on the past, right? This sum here, the sum of the SKI, the sum of the SKI. Right? Now, when you multiply this sum by that sum, so you're going to get, this is the expected value, right, of a whole bunch of things conditioned on the past. So you're going to get SKR, let's say when k is 1, so you're going to get when k is 1, S1I, S1I star, right, plus S2I, S2I star, so this, okay, until SNI, SNI star, plus now you are going to have cross terms, right? But the cross terms, because of the assumptions that they are uncorrelated, they will be 0. And similarly for the RQ. That's why the RS's and the RQ's are the sum of the individual R's, RS's and individual RQ's. Very good, okay. So I showed that. And the second thing I would like to show is that, of course, if you introduce a bound on the 4th order moment, then you get automatically a bound on the 2nd order moment, right? This is just restating the fact we already know. And what we are showing down here is that if the individual gradient noises satisfy these bounds for the 2nd moment and the 4th moment, the aggregate gradient noise will satisfy similar bounds. Okay, so the aggregate noise satisfies similar bounds. For example, this is the sum of the individual gradient noises. If the individual noises are 0 mean, the aggregate will be 0 mean, so it satisfies that. Now here, what is the norm squared under expectation? It will be this, the sum of the expectations of the individual norm squared, right? Because the cross terms will disappear. Now, if each one of them is bounded by that, the sum will be bounded by the sum of that, right? The sum of that. So this becomes a sum, this becomes a sum. So I don't really care about the form of these coefficients. The important thing is that there is a coefficient times omega squared, right? So if the individual gradient noises satisfy this condition, the aggregate gradient noise will satisfy similar conditions for some other constants. So this is for the 2nd order, okay? Right, so you understood where this came from, right? Because this sum here, Si of omega squared, under expectation, right, conditional, you can write it as the sum of the individual expectations, right? All cross terms will disappear, right? Okay. Okay, and here I'm just calling these coefficients by some other name. Okay, it doesn't matter what they are, it's just important to know they exist. What about this condition now? If the individual gradient noises have bounded fourth order moment according to this relation, does the same hold for the aggregate gradient noise? And why is it that I'm showing this? Because then the aggregate gradient noise would satisfy the same conditions we used before, and therefore I can write down the performance for the centralized solution directly from this from the results we had in previous lectures. So let's show that this is true, right, for the aggregate noise. Okay, so I can prove this result. I have the derivation on the next slide. It's not difficult. That if the individual gradient noises have the bound I showed on the previous slide, then the aggregate gradient noise, its fourth order moment will be bounded by something times the error to the fourth plus some other constant. I'm just telling you exactly what these constants are and calling them something else. I don't really care what these values are except that they exist, okay? So how do you get this result? Okay? So one way to get this result is as follows, you see. So the norm to the power 4, remember the aggregate gradient noise is the sum of the individual gradient noises. So that to the power 4. So now I can multiply and divide by n. I did not change anything. But remember that norm to the 4 is a convex function, right? This function here is a convex function. So I apply Jensen's inequality. Because this 1 over n, I have a convex combination of all these terms here multiplied, each one of them multiplied by 1 over n. So this is upper bounded from Jensen's inequality by 1 over n, the sum of the power 4 of these arguments. So n to the 4, that to the 4. But now each one of these to the 4, right? So this n to the 4, of course, comes out, n cubed. And each one of these is bounded by what we had before. Under a sum, you end up getting what I showed you before, right? You end up getting, so this is the n cubed, and then you end up getting these sums, right? So it's not difficult to get that. Okay, there it is. Okay, good. So now that I know that the centralized algorithm is a stochastic gradient algorithm whose gradient noise process satisfies the conditions that were required in previous lectures, then I can go back to previous theorems and just state them for this algorithm, okay? So I'm just reminding you here what is the MSD, right? Remember that the MSD essentially tells me what the mean square error is in steady state. Right? As I goes to infinity, what is this value here in steady state? I would like to find a first order approximation for it, first order in terms of the step size. Ignore the higher order terms. I just want to find out what the first order value is. And that's what this definition 52 is doing, like I explained last time, right? If you divide by mu, then the lim sup of that as mu goes to 0 converges to some value. If you multiply it back by mu, you are recovering that first order term, right? If you look up there, if you divide by mu, you extract the coefficient of mu, you will still have a term that depends on mu here. Then as mu goes to 0, this term disappears. And when you multiply by mu again, you recover this part, right? So I'm just reminding you, this is the MSD for the centralized solution, right? Just like what we did before. And what about the excess risk for the centralized solution? It's very similar to what we did before, except for a small difference. Okay? Again, the excess risk is the difference between the cost that I'm minimizing and its best value, divided by mu, multiplied by mu, except that now I'm dividing by n. In the centralized case. Why I'm dividing by n? This is just to normalize the results for the following reason. The aggregate cost now is the sum, right, is the sum of many individual costs, right? Is the sum of n of these costs. Okay? So if I want to compare the excess risk of the centralized solution to the excess risk of a non-cooperative solution, the excess risk of a non-cooperative solution is measuring a difference like this. Right? For that non-cooperative solution at agent K, its excess risk would be measuring the average value of this difference, right? For the aggregate cost, I have a sum of n of these differences, right? So it's an n-fold larger than that. So a fair comparison will have to normalize this by n, okay, to allow for a fair comparison, okay? And this becomes even clearer, for example, if all of these jks happen to be identical across the agents, right, then this difference here will be n times this difference. And when you normalize by, and then the comparison becomes fair, right, that I'm comparing similar quantities, right? That's why you have this n in this case, in the centralized solution. Very good, okay, so that's what I'm explaining on this slide, okay, that if they happen to be the same, then the global will be nj, and to compare them, you need to divide by n. Of course, like I explained in the last lecture, very often we use these simpler expressions, right? Rather than writing the expressions I showed you on the previous slide. These are approximate expressions. We just talk about the limit of the mean square error, the limit of the excess risk normalized by n. But these are to be understood in the form I explained before. Okay, very good. So now I can state the result. First, I'm reminding you, right? So H sub k is the Hessian at each agent k. Okay. G sub k, rather than write this extended matrix, from now on I'm going to use a compact notation for it. G sub k is the extended covariance matrix. It's the covariance matrix that needs to appear in the MSD expressions. In the real case, it is just RS. In the complex case, it is the extended matrix, RS RQ, RS transpose RQ star. So this is my notation from now on, okay? Fine. In the complex case, this is 2m by 2m. In the real case, it's m by m. Okay, so this is just definition. Very good. Okay, and now, because at least one of these is strongly convex, like we said, then at least one of them is uniformly bounded from below, then the sum is definitely positive definite, right? And therefore invertible. Because the inverse of this sum will appear in the expression, so I need it to be invertible. And this is the result. Now, you just go back to the theorem from the last lecture where I wrote down what the MSD of a stochastic gradient algorithm is. What did I say there? I said that it will be mu over, okay? It will be mu over 2h. The mu here is mu over n. So that's why the mu here is mu over n. The expression you had from last time, it was mu over 2h, right? H is 1 for okay. So it's mu over n. And then here you had the Hessian inverse, but the Hessian here is the sum of the individual Hessian matrices. And here you had that extended covariance matrix, which is the sum of the individual covariance matrices. That's it. And again, from that theorem, the convergence rate is 1 minus 2 mu c. This is the lower bound on the aggregate cost. And then you had the step size over h. Okay? Here I just wrote down exactly the previous result from the last lecture for this case. Okay? Once I know what the Hessian matrix is and what the covariance of the gradient noise is, I just write it down. More formally, this is the statement. Okay? More formally, that was a colorful summary of what comes next, right? That for small enough mu, the mu here, the mu prime is mu over n, and this bound comes from the previous theorem, and the bound was in terms of the nu and the delta and the beta. This is the beta for the noise, upper and lower bounds on the Hessian, and the reason I add this c just to say these are parameters for the aggregate cost in the centralized solution. And the error vector converges at the rate alpha, right? This is what we showed before, I'm just writing it here. Okay, and the convergence rate is this. This is the first order term in mu, and that the error converges to a region of size mu, And actually, we can be more explicit and tell you exactly, right? Find the first order approximation for that region, plus higher order terms. I can find the first order approximation for the excess risk, plus some higher order terms. I'm just writing down what we proved before, right? Okay, and these terms here, the excess risk and the MSD, they are given by these expressions, which we derived last time. Because the excess risk was mu, so that's mu over n, h over 4, and you have an additional n because when we defined the ER for the centralized, we added that additional n. That's why you end up with n squared here, trace of the sum of RS. Fine? Okay. So what I did so far, I introduced, right, the problem of minimizing an aggregate cost, okay, which is the sum of individual costs, okay, and I assume that this cost is strongly convex, and then I applied a stochastic gradient algorithm to it with the step size mu over n, right, and then the sum of the individual approximations, okay, and then I showed you what the results are, what the performance results are in terms of the individual Hessian matrices and the individual gradient noise covariances. Very good. Okay, and that the convergence rate, okay, will be given by, this is again the same expression, this is a first order approximation, first order mu of the convergence rate, okay. Okay, so you see, in the non-cooperative case, the convergence rate, if I'm not mistaken, was something like this, 1 minus, let's see, 2 mu lambda min of h, something like this, if I'm not mistaken, okay? Let's assume that all the Hessian matrices are the same across the agents, okay? If they are the same, then this sum becomes n times h, and the lambda min is n times the lambda min of h, and then that n cancels that n. So that's why the step size in this centralized case has to be mu over n, so that the convergence rates match each other, right? Okay? Okay? Understood? Okay. Now, this is just the remark that I mentioned before. Rather than introduce the conditions on the individual gradient noises, assuming that they are zero mean, bounding moments, and then circular, they are circular and uncorrelated, I can introduce the conditions directly on the aggregate noise. I can do that directly, okay? That's what this is saying. You can do that directly, and then, of course, you apply the result of the theorem. Okay, so you state the conditions directly on the aggregate noise. Yeah.
When we make these assumptions, we implicitly say that they are uncorrelated.
No, it doesn't necessarily mean, right? That's what I'm saying. Okay, if you want to do away with these conditions that they are uncorrelated and circular, then introduce the assumptions directly on the aggregate noise, right? Then it becomes a standard stochastic gradient algorithm. Okay. The only thing that will happen now is that the gradient noise covariance here is not anymore the sum of the individual gradient noises, right? That's all, because the uncorrelated conditions and the circular conditions allow that. So what will happen now, you see, of course, the Hessian is still the sum of the Hessians, but the gradient noise, right, it will have a form, of course, like this. Right? But these RS, this RS, and this RQ, they are not necessarily anymore the sum of the individual RS is the sum of the individual RQs. So all I'm saying, then you will end up getting results expressed in terms of these quantities. That's all. You see? Before I was able to say, okay, that under these conditions, the uncorrelatedness and circular conditions, the GC is the sum of the individual G. That's the only difference, okay? Fine. So now let's go back, okay? So now that you understand what a centralized algorithm is and how it performs, let's go back and perform a comparison with non-cooperative agents in the general case, okay? Before I did this comparison for you, for the mean square error case, but I want to show that similar conclusions hold for general cost functions, not just mean square error cost functions, okay? So here it is. I again have independent non-cooperative agents, each one of them running a stochastic gradient algorithm, okay? But now, in this case, for the comparison to be meaningful, I have to assume that all these individual costs have the same minimum, right? I use this notation W sub k of O to indicate the minimum of J sub k, okay? But for a meaningful comparison, now I have to assume that all these agents are working on the same problem, estimate the same omega 0, okay? Very good. So they all have the same minimum. And each one is running its own algorithm. Okay. And that each cost is strongly convex. Okay. Let's assume that because I would like each problem to be well defined for that individual agent, to have a unique minimum at omega 0. So now I have to assume that each individual cost is strongly convex. I did not need that assumption for the centralized solution, right? So let's assume that each cost, right, with parameter nu, so the Hessian of each individual cost is bounded from below by nu. So the Hessian for the aggregate cost is bounded from below by n times nu. That's all. So I'm just saying that if this is the setting, then you can choose this nu c to be n times nu, right? Okay. Okay. So, if you go back to the theorem, we wrote down that the convergence rate is, in the previous part of this lecture, when I derived the theorem that identifies the convergence rate for the centralized solution, it was given by this expression here. Mu over n was the step size, and nu c was the lower bound. Well, since nu c is nu times n, the n cancels out, and you see you end up getting the same expression as the non-cooperative solution. So this again confirms the remark I mentioned before, okay, that by choosing mu as mu over n, right, the centralized solution and in the non-cooperative solution will converge at the same rate to first order in mu, right? So we don't have, so the convergence rate is set. So let's now compare the performance levels. Okay. Okay. So what is the average non-cooperative performance? You have to average the performance at every agent k, right? This is just notation, MSD, non-cooperative at agent k. What is the MSD at agent k? Well, we know it is the trace, the inverse of the Hessian at agent k, the noise covariance at agent k. Okay, gradient noise, G for gradient noise, okay? And this is the coefficient that always appears, right? Okay, so remember, the non-cooperative solution is running a gradient descent algorithm with step size mu. The centralized solution, mu over n. Okay, so this is the average, so I can take this out, here it is. The sum of the trace is the trace of the sum, right? So in the general case, for general costs, remember in the mean square error case, if you recall, this term here looked like this, mu m, and then the average of the noise. Remember? In the mean square error case, we obtained an expression that looked like this. In the general case, it looks like 79. Okay, because things here do not simplify like they simplified in the mean square error case. I still have because the Hessian matrix had an RU in it, and this had an RU in it, they cancelled, okay. Very good. But this is the general case. Now, let's look at the centralized solution. Okay. Sorry, so here I'm just repeating what I had on the previous slide. The non-cooperative expression is the first line, okay. In the general case, okay, so there is a small typo here. This should be star, right, because I'm talking about the general case, okay. So the average non-cooperative performance, this is what I just wrote on the previous slide. And this is the performance for the centralized solution that we derived, right? It is the inverse of the aggregate Hessian times the sum, right, times the aggregate gradient noise. So compare. Here you have the trace of the sum of these products. Here you have the trace, you invert the h's, and then you times the sum. Now, I'm going to show you some simple algebra is going to show you that this expression is always smaller than that expression. We already saw this in the mean square error case, because we found that this expression here looked like something like this, mu over m average of the noise, right? Okay, this expression here looked like mu m 1 over n, and then 1 over n again, right? If you remember. So in that case, it was easy to see that this is smaller than that by a factor of n. Here, I need some algebra, okay? So let's prove that, and this is now just a matrix problem, a simple problem. Prove that this is smaller than that. Okay, so let's prove it. Okay, so this is the statement. So I want to show that the centralized solution always outperforms the average non-cooperative solution. But it doesn't mean that it outperforms every individual solution, right? So this is the proof. Remember that G sub k is a covariance matrix, so it's non-negative. HK is positive. Because here we are assuming, right, that each J sub k is strongly convex. So each H sub k is positive definite. Okay. Now, if a matrix is non-negative definite, you can always factor it like this, as some matrix times its conjugate transpose. Okay, for example, introduce, because U is Hermitian and non-negative definite, let's introduce its eigendecomposition, U lambda U star, right? Lambda will have non-negative eigenvalues, right? Non-negative eigenvalues. So I can write this as U lambda to the 1/2, split the lambda, right? Okay, and then just call this L star, right? Something like this, LK star. If the lambdas have some zero eigenvalues, right? If lambda has some zero eigenvalues, right? Let's say I can write this like this. This is U1, U2, lambda 1, 0. I put the zero eigenvalues at the end. U1, U2, something like this, right? And then, so this becomes something like U1. So now U1 is not square anymore, right? But it doesn't matter. Now split lambda 1, and you end up getting LK star, where LK will be full rank now. That's all, okay? So this factorization, it's not difficult to understand that every non-negative definite matrix can be factored like that, okay? This is just like when you say every positive number, you can write it as a number times itself. This is the extension to the matrix case, that every non-negative matrix G, you can write it as some matrix times itself, but actually the conjugate of that matrix. Because technically, you see here, over the set of complex numbers, you can write this as 2e to the j theta times its conjugate. You can do that for positive numbers, right? So this is the extension for matrices, okay? Very good. So now, every G, I can write it like this. Very good. And then remember this property that for trace, I can always switch the order of the matrices, right? Okay. So let's go back now. The non-cooperative expression was the trace, it included this, the sum of HK inverse GK, right? Okay. It was the trace of that. Now I'm going to replace GK by the factorization LK star, right? And because this is a trace, I can move this LK and put it before the HK inverse, right? I can move this and put it here before. Okay, so that's what I did in the first expression, right? So this is still the MSD for the non-cooperative solution, okay? The sum of LK star HK inverse LK. Fine so far? Okay, let's look for the centralized solution. I had the trace of HC. HC is the sum of the H's. Let's just call it HC, okay? times, okay, HC inverse times the sum of the GKs, right? This is what I have in this centralized case, right? The sum of the GKs, and this is HC inverse. Okay. So this is the trace of the sum of HC inverse LK star. I brought this sum here. Put H, okay? And then again, I can bring this LK star there. So this is what I did here, you see. So I was able to rewrite both expressions in very similar forms with the same LK multiplying from left and right. But here you have HK inverse, here you have HC inverse. And remember, HC is the sum of the HKs, right? Right, so HC is the sum of the HKs. So if I subtract these two, you get this expression that you have here, 84, right? HK inverse minus HC inverse. Now, obviously, you see, this H, so what is this difference here, right? Just think about it. This HC, right, is larger than any individual HK, right? This HC is larger than any individual HK because these HKs are all positive definite, right? So when you invert that relation, right, it becomes that the HK inverse minus HC inverse has to be positive definite, right? So this has to be like that. And then you conclude, so we showed then that the result holds even in general, right? Very good. Now, in the mean square error case, I showed that the improvement in performance is a factor of n. What about in general, right? What about in general? Do we still get a factor of n? So this is to show you an example first. Let's take an example where all the h's are the same, meaning all the individual costs, they are not necessarily the same, but have the same Hessian matrix. Okay, for example, even mean square error costs with the same RU, but not, okay, with the same RU, will satisfy this, right? Well, this is what we saw before. Okay, now, in this case, when the H's are the same, okay, sorry, okay, yeah, so let's go to the example here. So when the H's are the same, then what would be the HC? N times this H, right? The global Hessian matrix is N times the individual, okay. And then it appears inverted, right? So HC inverse will be 1 over N H inverse, right? Okay, so that's why you get this additional 1 over N and H inverse here. But when you write it like this, right, this is exactly the performance of the non-cooperative solution, okay? So you can see that in this case, when the Hessian matrices are uniform across the agents, the centralized solution will always will again give you n-fold improvement, okay? So let's look at another example. So this is another example, okay? In this case, I'm assuming that the Hessian matrices are not the same, but multiples of the identity, okay? These are just examples to show you a different point of view, okay? And I'm assuming that the noise covariances are uniform. So in this case, I'm assuming the noise covariances are uniform. For example, this situation comes up in the mean square error case, because in the mean square error case, what was the HK? The HK was RUK, or 2RUK, right? And the covariances of the noises, I think in the real case, it was something like this, sigma VK squared RUK. This is what you have in the mean square error case. Now, if I want the HK to be a multiple of alpha, then just to choose this RUK to be of this form, a multiple of the identity, right? Then the HK will be a multiple of the identity. Okay, if this is a multiple of the identity, right? So choose this product to be some uniform value, then this condition is satisfied, right? So I'm just showing you an example where this condition is satisfied. Understood? Okay, so the Hessian matrices are multiples of the identity, and the gradient noise covariances are uniform across the nodes. Okay, so here it is. I'm showing you that this happens in the mean square error case. Okay, for particular, of course, if you choose this product to be a constant. In that case, if you go back to the expressions for the non-cooperative case and for the centralized case, just go back and plug in, right? Just to remind you, what are the expressions? It's some constant. In one case, it is the trace of the sum of HK inverse GK, and in the other case, it is the trace of the sum of the HK all inverse the sum of the GK, right? Up to some constants here, right? The important thing is how these calculations are done inside the trace, right? In the second case, you first add up the H's, invert them, and then multiply by the sum of the G's. In the first case, you multiply each inverse by G first and then add them up, okay? So in this case, we know what each HK is, alpha times I. We know what each GK is, right? So just substitute into these expressions, then this is what you are going to get in this case. Okay, I showed you on the previous page, right, what each HK is, what each RSK is. This sigma is the constant value you set here, right? So if you just substitute these values into these expressions, you'll find that the centralized solution is given by this quantity. You get here mu over n, m sigma squared, the same quantity there, mu m sigma squared for the non-cooperative case. But what you get down here, in one case you get the arithmetic average of these alphas, in the other case you get the harmonic mean of these alphas. Okay, arithmetic mean and harmonic mean. Smaller. So if you divide them, if you divide this by that, you'll find that the performance depends on the ratio. Okay, and because the harmonic mean, right? So you can see here, right, that the harmonic mean is always smaller than the arithmetic mean, right? So in this case, so this ratio here is always less than or equal to 1. So you can see that the performance, right? So it's not necessarily n times fold, right? It can be lower than that, but okay. Fine? Okay. This is another example. This is a simple example. Let's assume that I have a collection of n learners, okay? N learning machines. And each one of them is seeing data x, meaning, for example, seeing labels gamma ki and feature vectors hki. The gammas are class labels, plus or minus 1, and the hk's are feature vectors. So I group them into and call them x. So if you want to minimize a risk function, an aggregate risk function, which is the sum of individual costs. And so in this particular case, I'm assuming that which is the sum of individual risks. I'm assuming that the individual risks are all uniform in this case, in this example, because it is Q here, equal to the average of some loss, right? The average of some loss. Okay, so Q is the same, but here you have the data at agent K. So this would be the centralized solution, right, in this case. Correct? The centralized solution is that. The individual gradient noise is the difference between the true gradient, okay? Okay? Yeah, this is for so I'm assuming that the individual J's are the same. This is what, okay, I'm calling it J of omega, okay? So the difference between the true gradient and the approximate gradient. of course, because in this particular case, all of them will have the same minimum because the cost is the same. Okay, so this is the gradient noise. It's given only by the gradient of the loss function and its covariance. Okay, the covariance you can get it from by computing the expected value of this in steady state. Okay. Okay, very good. And then if you go back to your expressions, okay, and you substitute, right, your RS, you will find that the excess risk is given by this expression. Okay, just go back and substitute this. Okay, so this is just an example to illustrate the expression for the excess risk of the centralized solution. It only depends. This is the case of real data, so you don't have extended covariance. It's only RS. Okay, if you go back to the expressions, this is what you will get. Okay, and if you are interested in the MSD, you can also get it. Okay, fine. So now let me consider this case, okay, which will serve as a motivation for what will come next in the course when we study networks. Let's assume now that I have, let me show you the figure first. I have a fully connected network, okay? Here I'm showing you n agents, but each agent is connected to everybody else, okay? So this is a fully connected network. And let's assume that the following happens, okay? Every agent sends its information, right, to every other agent, okay? So every agent in this fully connected network, you can think of it as a fusion center by itself, because it has access to all the information from all other agents. Meaning that it knows the approximate gradient vector that's computed by every other agent L. Therefore, every agent K, rather than run a non-cooperative algorithm at its location, every agent K can run a centralized algorithm at each location, right? Because it has access to all the information from all other agents, and therefore it knows what these approximate gradients are. Okay, so in a fully connected network, in principle, the algorithm can do this, right? Every agent can run a centralized solution, and therefore every agent will be able to attain the performance of the centralized solution, right? Good? Okay. Now, if you look at this implementation, okay, so if you look at this, here it is also. If you look at this implementation, here I'm assuming real data, but more generally you can put a star here just to make it more general, okay? What pieces of information the agents are sharing here? In this implementation, you are assuming that every agent is sending to the other agents how it computes its approximate gradient vector, right? Okay. But of course, agents could share other pieces of information, more or less, right? So this is one item we'll be discussing when we talk about processing over networks, right? What information you share is important, right? And you may not need to share as much information as you have in this case, okay? Number one. Number two, you can see that what agent K is doing, it's combining the information that it receives from the other agents, like you said, in a convex manner, and giving them equal weight, 1 over n. Each one of them is receiving, right? I get the gradient vector from each one, I weigh them by 1 over n and combine them, right? There is no reason why you should give equal weights to all agents. You may want to give more weights to some agents and less weights to other agents, right? Especially if you know that some agents are noisier than others, or if you suspect that somebody is malicious, right? You would like to give very little weight or no weight to that link. Okay, so what would be the effect of allowing the weighting here to change? And not only that, every agent would use different weights. Agent 6 would use a collection of weights. Agent 4 may use a different collection of weights. As long as they add up to 1, that's okay, right? Okay, so that's another item that we will be discussing when we study networks, right? How do we choose these weights, and what's the effect of the weights on the performance? Okay. More importantly, right, do I really need to receive information from every other agent to be able to attain the performance of the centralized solution, right? This is a deeper question. So, does every agent in this network need to receive information from every other agent so that each one of them will be able to attain the centralized solution? And you will see later that, okay, we can attain the performance of the centralized solution even using a sparsely connected network. 4 may be connected to only a couple of neighboring agents, 3 a couple of other neighboring agents. As long as the network is connected, meaning you can find a path between any 2 agents in the network, but not necessarily fully connected. It can be sparsely connected. You may have, let's say, a network with 1,000 agents, 1,000,000 agents, but the topology is sparse. But as long as it is connected, we will be able to devise algorithms that will allow these agents to attain centralized performance by performing only locally. So these are questions that we'll be addressing before, okay? So these are the 3 points that I just mentioned here, right? The first is that each agent is receiving the gradient vector information, but of course other pieces of information can be received. The second point is that the combination coefficients, they do not need to be 1 over n. And the third point is that you don't need to receive information from everybody around you, from everybody in the network, okay? Of course, these statements require, and that's what we will be doing in the later half of this course, answering these questions in some detail, okay? So for example, let me show you the figure and I'll come back to these questions here, okay? Of course, this is a simple network. I only have 5 agents, right? But think of, let's say, a network with thousands or 1,000,000 agents, right? This is just a simple figure. So this is the non-cooperative case. Each one is working on its own, trying to estimate something. Or they can be fully connected, right? And each one is sharing its information with everybody else, and each one can run a centralized solution. With today's lecture, you already know how the performance of this compares with the performance of this. You know exactly how much you gain, right? You know that the average performance here, the performance of each one is better than the average, okay? But not necessarily better than the individual, okay? But now, there are many other topologies that can connect the agents. For example, this is one topology, this is another, this is another, this is another. These are not fully connected topologies. Of course, because I have a very few number of agents here, it looks like they are well connected. But if you have a huge number of agents, the network will be much more sparse, right? The question now that we can ask the following questions. Given a variety of topologies connecting the same agents, right? These are the same agents trying to solve the same problem. Since I have a choice of topologies, okay, which topology will have best performance? Does it matter? Does it make a difference how I connect the agents? Which one will give me the lowest MSD and the fastest convergence rate? We are going to answer. I'm not going to tell you the answers now, right? Each one of these questions, by the end of this course, you are going to have an answer, a specific answer. And then, given any connected topology, can I make its performance match the centralized solution? How do I choose the weights, the combination weights, to enable that? So this is my second question. Third question, which aspects of the topology influence performance? Okay. What's special about a topology that influences the performance, okay? And which aspects of the combination weights influence performance? So not just topology, not just how the agents are connected to each other, but what weights they will be using on these links also influences performance. In what way? Okay? Can different topologies be made to deliver similar performance? Can I always make different topologies over the same nodes deliver the same performance? Is cooperation always beneficial? Does it always help to let these nodes work together? Okay? And then if the individual agents, for example, in the non-cooperative solution, if the individual agents know how to solve the problem, each one runs a stochastic gradient algorithm, knows how to get to WO, right? And now I connect them with a topology. and I run an algorithm over that topology, will it follow that the network will be able to solve the same problem? It will depend on how you run the algorithm, and okay, so you are going to see the implications of this, okay? So these are the questions that by the end of this course, you will have specific answers to them, and they are all very important questions, right? Which topology has best performance? Which aspects of the topology influence performance, right? Is cooperation always beneficial? Can different topologies deliver some performance, the same performance? What do you think? Guess, take a guess.
Yeah.
Okay, that's an intelligent guess, right? Maybe. Okay. Okay, anyway. So let me conclude this lecture by talking about the decaying step sizes case. Everything I talked about so far focuses on constant step sizes in this lecture, right? And that will be the emphasis in this course for the reasons I explained many times, because I'm interested in adaptive and learning solutions, right? But nevertheless, it's important to also talk about the decaying step size case, because like I said before, when the step size mu of I goes to 0, right, and satisfies the two standard conditions that we impose, that this diverges, but this converges, or this is one set of conditions, another set, you keep this and you replace this by that, right? You can show that omega converges to omega 0 almost surely, or in the mean-square error sense. So convergence occurs, right? The MSD goes to 0. Okay. However, you lose adaptation because the step size kills the update after some time, and the convergence rate will not be geometric, right? Will be at a rate of 1 over I, which is much slower, okay? So again, you see, this is a stochastic gradient algorithm. A stochastic gradient algorithm where the gradient noise satisfies the conditions I spelled out earlier, and therefore I can go back to the previous result and state it in this context. So I have two possible choices for step size sequences, those that satisfy the first condition or the second condition. Of course, if the step size sequence satisfies the second condition, this implies the first. Because if the sum of the mu squared is finite, then mu is going to 0, okay? And if you remember, earlier I gave you a convergence result for the stochastic gradient algorithm under these conditions. That same result applies here in the centralized case, and this is the statement of the result, okay? So I have an aggregate cost which satisfies the usual conditions, Asian matrix bounded from below and from above, okay? Then I have two conditions here, right? 102 is when the limit, sorry, there is a typo here, right? This limit here should go to 0, right? This is a typo, I have to fix it, okay? Okay, so now 103 is the condition where the sum of mu is infinite and the sum of mu squared is finite, okay? This is the second condition here. In this case, you can show that W converges to WO almost surely. So the probability of that event of WI converging to WO is 1. In the second case, okay, in the second case, so this is a stronger condition. In the second case, which is a weaker condition, and then mu goes to 0. For example, sequences of the form 1 over I satisfy both conditions, right? You don't need to satisfy this and or satisfy that. So for sequences like this, you get this type of convergence and that type of convergence. But there are other situations where you may satisfy this, right, and not that. So here you get almost sure convergence, here you get mean square error convergence. And not only that, okay, for this particular sequence, 1 over I, the one I just explained, or some constant over I, tau c, you can show at what rate convergence occurs. Okay, so for example, you have 3 possible rates of convergence. The best one is the first one because convergence occurs at 1 over I. In the second, it occurs at a rate of log I over I. And in the last one, it occurs at the rate 1 over I to some power, and that power is smaller than 1. Okay, this power here is this number that you have here. It's smaller than 1. So if this condition is satisfied, what is this condition, by the way? This condition is the lower bound on the Hessian. That's just a constant, right? H is 1 or 2, N is the number of agents. But the important fact is that it depends on this tau C. Okay, tau C is this constant here in mu. So that tau has to be large enough for you to get the fastest conversions, okay? It has to be large enough. If you choose it too large, you may get an overshoot and then the algorithm converges, okay? But it depends on tau C. So if you choose your tau C large enough, you can attain convergence, and the fastest you can get is at the rate of 1 over I, whereas in the constant step size case, it was some exponential rate, right, alpha to the I, but you get an MSD, which we characterized, okay? Fine? Very good. So that's what I wanted to discuss with you today, right? So today, that essentially covers part 3 of the course, right? The centralized solution, right? How to characterize its performance when the step size is constant, when the step size is decaying, and how to compare its performance with the non-cooperative solution. We found that the performance is always better than the average non-cooperative solution, right? And then I considered several examples where I showed, for example, in the mean-square error case, you get an n-fold time improvement, right? And then so we studied today 2 scenarios where there are extreme scenarios. One, I have a collection of n agents non-cooperatively performing and solving an adaptational learning problem, right? So they are not cooperating with each other. The other extreme scenario is where every agent has access to all of the information over a fully connected network or a fusion center, right? And we characterized how the performance compares in both cases, right? Starting from the next lecture, I'm going to focus now on the network scenario. I continue to have a collection of agents that are connected, but the topology is not necessarily fully connected. It's more likely to be sparsely connected. So what are the limits of performance in that case? How do I choose the combination coefficients? How do I characterize the influence of topology on performance? Because now the topology becomes important, right? Okay, so that's what we will be doing in the next part of this course. Okay, so do you have any questions? No questions? Okay, very good. Thank you. So we'll finish here today.